A small airplane leaves an airport on an overcast day and is later sighted 215 kilometers away in a direction making an angle of 22 degrees north of due east. Sketch the position vector representing the location of the airplane relative to the airport, and what are the x and y components of the airplane's position vector? Okay, so there's a bit of information here. They're giving us the position of the airplane relative to an airport. So let's go ahead and represent that position with the vector r. So we will say that r vector is equal to some distance away from the airport at some angle, 22 degrees. So r vector equals r at 22 degrees. Now I am labeling the magnitude of r to be 215 kilometers, and the direction is 22 degrees north of due east. So I'll just add that little detail so I'll remember to put this in the correct quadrant. Now, again, I usually like to do problems graphically first if I have the information, and then work it algebraically. So I'm going to go back to our coordinate system. I like using graph paper. So again, I like to draw things out graphically before I solve them algebraically. So in sketching this, we're going to use a rectangular coordinate system. Our rectangular coordinate system will have an x-axis, which will be horizontal. The scale will be in kilometers, and we'll have a y-axis, which will be vertical, and the units of the y-axis will also be in terms of kilometers. Now, I don't think the graph paper is going to really help me out a whole lot. Maybe it will. We'll see. But if I'm going to graph this first, I'm going to try and make our graph as close to reality as possible. And let's go ahead and draw a vector that is 215 kilometers away. Maybe before we draw this vector, maybe we should specify what our scale is. That would probably be helpful. So in specifying our scale, I will just say every 5 divisions corresponds to 100 kilometers. So this is 100 kilometers, 200 kilometers. So 215 kilometers on the x-axis would be approximately right here. And then we'll have I'll just do the 300 kilometers here. And then vertically, we have 100 kilometers, we have 200 kilometers, we have 300 kilometers. So if I were to imagine what a distance of 215 kilometers would be from the origin, and we will say the origin corresponds to the airport. So in imagining what 215 kilometers would be according to this scale, I'm going to try my best to do a quarter of a circle. And this quarter of a circle has a radius of 215 degrees. And this quarter of a circle is only to help me kind of come up with a rough sketch of where I need to place my vector. So the vector is going to extend from the origin to the edge of that quarter circle. Now I need to do the angle. Now, if I didn't have a protractor, I would kind of guesstimate what the angle would be. And I think I would guesstimate that 20-ish degrees would probably look something like around there. But we could do better than that because we have a protractor. So I'm going to go ahead and fire up the protractor, and let's go ahead and use it to help me figure out 22 degrees. So 22 degrees is about right here. And notice the distance on this. So what you're seeing with my protractor tool, that first coordinate corresponds to the distance, and the second coordinate corresponds to the angle. And actually, I'm feeling pretty good with my guesstimate. Like, see how my quarter circle, see how that is basically what my protractor was telling me was 215 units approximately. And notice how my angle that I guesstimated is pretty close. So guesstimates are just that, and the purpose of them is just to help you get a good feel for the problem. But now that I know that my vector looks like this, and let's go ahead and label this vector. This is vector r. We can now look at this and come up with, from this picture, come up with a strategy for how to determine the x and y components algebraically. So again, this is our position vector. So algebraically, remember, the x component is a one-dimensional vector that is parallel to the x-axis. So that's about right there. And the y component is also a one-dimensional vector, which is parallel to the y-axis. So there are the components of my vector. So if I were to look at this roughly, I'd probably say that the x component of vector r is 200 kilometers, and the y component of vector r is roughly, that looks to be about 80 kilometers. So I am going to just write that to the side. I'm going to use this later as a reality check for my actual algebra. So, excuse me. So for my guesstimate, I'm saying the position of the airplane is roughly 200 kilometers along the x-axis and roughly 80 kilometers along the y-axis. So now that I have my rough guesstimate, I'm going to actually determine this algebraically. And algebraically, hopefully, our answers will be pretty close. So to determine it algebraically, we have a few bits of information that I'm going to add to our sketch. We know what the angle is. The angle is 22 degrees north of due east. And as a reminder, if you don't remember the compass rose goes north, south, east, and west. So my north axis is really my y-axis, and I'll put that here as a reminder. And my east axis is really my positive x-axis. So 22 degrees due north of east is just how I drew it, above the positive x or east axis. I am going to label this as theta r in my sketch. So we have a right triangle, and we know, because we've had trigonometry, how to calculate the legs of the right triangle. Remember, the components of a vector just corresponds to the legs of that vector. So I am going to indicate the x component as r1, at least the scalar part of the x component is r1, and the magnitude of the y component of that is r2. There's my right triangle. That is just a little sketch to remind myself of right triangles. And I know how to calculate legs of right triangles by using trigonometry. So in this right triangle, and let me just redraw it one more time, or not even redraw it, let me just add the 215 kilometers right there, and let me add the 22 degrees right here. So with right triangles, you know trigonometry. Now, as a reminder of our trig, we know that a side that is opposite to an angle can be found by using the trigonometric function sine. So R2 is going to be equal to the hypotenuse, which is R, times the sine of that 22-degree angle. So that component then is R2 is equal to 215 kilometers times the sine of 22 degrees. So let's see what the value is of that, and I'm going to have to get my calculator for this. So I have 215 degrees times the sine of 22. I need to make sure my calculator is in degree mode. Right now it's in radian mode, but I was given an angle in degrees, so I'm putting my calculator in degree mode. So again, 215 kilometers times the sine of 22 degrees. I end up with to two significant figures, I end up with 81 kilometers. So notice how our estimate up here, we set the y component for our estimate was going to be 80 kilometers. And that was just a rough sketch, kind of a rough sketch. And when we do the algebra, we get 81 kilometers for our y component. That's great. Our sketch is confirming our algebra. Now let's do the x component. So the x component is this horizontal leg of the right triangle. Now remember from trigonometry, a side adjacent to an angle can be found with the help of the function cosine. So we're going to say that adjacent side, R1, is equal to the hypotenuse, R, times the cosine of our angle. So we have R1 is equal to 215 kilometers times the cosine of 22 degrees. Let's enter this in our calculator. 215 kilometers times the cosine of 22 degrees equals to, we'll just round it to the nearest ones place for now, but that is equal to 199 kilometers. Wow, that's pretty darn close. Remember, my estimate with the graph was 200 kilometers for the x component. Algebraically, we get 199 kilometers. I'm feeling pretty good. So now that we know what the components are, we could write this. Well, the question for part B, what are the x and y components of the airplane's position vector? So we would write the x component as a vector, because components are vectors. I am going to write R1 is equal to 199 kilometers I hat. Remember, I hat corresponds to the x-axis. And R2 is equal to 81 kilometers j hat. So those are the components of the x and y components of our position vector R.